Alright, so today we're going to be looking at the combined gas law. Really, we're taking the work of Charles, Boyle, Gay-Lussac, and we're going to take those three separate equations, make one equation with them. Now, those three researchers were always trying to control for the third variable. For instance, Boyle worked with changes in pressure and volume, so that means temperature was kept the same. Charles worked with volume and temp, so he had to keep pressure the same. Gay-Lussac worked with pressure and temperature, and he had to keep volume the same. In real life, though, we can't always control for these things. So we have what's called the combined gas law. It's up there on your screen right now. So starting pressure times starting volume over starting temp equals ending pressure times ending volume over ending temp. Now the temperatures I have starred because we have to remember to change our temperatures into Kelvin. And to do that, you just have to add 273 to whatever Celsius you have. If it's already in Kelvin, you don't need to convert it. Alright, so here's how this equation kind of looks in practice. So there at the bottom, it's a little bit small and I can't change the font. But if I initially have a gas at a pressure of 12 atmospheres, alright, so initial gas pressure is 12 atmospheres. So P1 equals 12 atmospheres. A volume of 23 liters, so that's my V1. And a temperature of 200 Kelvin. Alright, so they're already giving us the temperature in Kelvin, so that'll work just fine. They then raise the pressure, so we have a P2. They raise the pressure to 14 atmospheres. And then they increase the temp to 300 Kelvin. So let's keep my variables in the same order. And then the question asks, what is the new volume of the gas? So what we're looking for is V2. All right. 6 variables, we know 5 of them, so let's go ahead and plug them into the formula we have. So we have P1 times V1, or we have 12 atmospheres times 23 liters, and that's over T1, which is already in Kelvin for us, so 200 Kelvin, and that equals P2, which is 14 atmospheres, times V2, which is what we're looking for. I like to leave that V2. And that's over T2 here, which we said was 300 Kelvin. All right, so now I need to get V2 by itself. There are a number of ways you can do this. Personally, I like to get all of my numbers set up first before I do any math, but you can start doing the math before you do the algebra. You could take 12 times 23 divided by 200 and set that equal to whatever 14 divided by 300 is. That's fine. Personally, I'm going to get my variable by itself, and then I'm going to do my multiplication and division. All right, so right now we have V2 being divided by 300 Kelvin. So to get, the first step is to get rid of this. So the opposite of divided by 300 Kelvin is to times by 300 Kelvin. And what you do to one side, you do to the other. All right, so now I have V2 times 14 atmospheres. So I'm going to have to do the opposite of that, which is dividing by 14 atmospheres. And what you do to one side, you do to the other. All right, so now I have V2 by itself. That equals 300 Kelvin times, what was it, 12 atmospheres. Got a little sloppy with my writing up there. Times 23 liters. I'm going to put that in parentheses so I know that gets done together. All over 14 atmospheres times 200 Kelvin. Put that in parentheses, make sure I do my math right. All right. Kelvin on top, Kelvin on bottom. Kelvins cancel. Atmospheres top and bottom. Atmospheres cancel. So I'm left with liters, which is what volume's in, so I know I'm doing that part right. So now, if I come down to my calculator, so I have 300. I can't see some of that. All right, times 12. Times 23. Oh, there's no parentheses on here. That's scientific. And we're going to start over. All right, so 300 times 12 times 23. Still no parentheses on here? All right, that's fine. Divided by 14 divided by 200. All right, so the answer I get for V2 is 29 point, I'm going to say 6. Bless you. And once again, my unit there is liters. All right. So, pressure increased, temperature increased, volume increased a little bit. And really that increase in volume, the increase in pressure should have decreased the volume, but we only increased it by 2 atmospheres. Whereas the increase in temp would have raised the volume, and we increased the temp by 100 Kelvin. So that means that the total volume of this thing increased roughly 6.6 liters. All right, so let's do one more example. Let's go with that guy there. All right, let's go edit clear. All right, and I'm going to write maybe a little bit smaller. All right. So this question is: a gas takes up a volume of 17 liters. Okay. V1, 17 liters, has a pressure of 2.3 atmospheres, and a temperature of 299 Kelvin. If I raise the temperature to 350 Kelvin, and lower the pressure to 1.5 atmospheres, what is the new volume? All right, this one we're going to set up just the same as we did last one. So we're going to have 17 liters times 2.3 atmospheres over 299 Kelvin equals V2 times 1.5 atmospheres all over 350 Kelvin. All right, so now to get it set up, we just got to do the opposite of what's happening in V2 right now. So the first step, we're being divided by 350K. So we're going to have to do the opposite of that. And what you do to one side, you have to do to the other. And we're timesing by 1.5 atmospheres to the V2, so we have to do the opposite of that, which is dividing by 1.5 atmospheres. And what you do to one side. All right, so now we have V2 equals 350 Kelvin times 17 liters times 2.3 atmospheres all over 1.5 atmospheres times 299 Kelvin. And once again, we got Kelvin top and bottom, so those cancel. Atmospheres top and bottom, so those cancel. So we got 350 times 17 liters times 2.3 divided by 1.5 times 299. All right, just plug that in. That'll give you the answer. But let's go through, what if we need to find temp? Let's see if I can find one of those. Is there one of those? There we go. All right, so this one. So I have 2.9 liters of gas. Should be a point there. Pressure of 5 atmospheres. And a temp of 50 degrees Celsius. All right, first things first, that's Celsius. Let's convert it to Kelvin. Okay. And they want to know the temperature. So T2 is what we're looking for. They decrease the volume to 2.4 liters. And they decrease the pressure to 3 atmospheres. All right, so now when I set this one up, I have 2.9 liters times 5 atmospheres over 323 Kelvin equals V2, 2.4 liters times 3 atmospheres all over T2. All right, so now what I'm looking for is in the bottom. The first thing I have to do is cross multiply. So I need to bring this T2 up here, and 323 Kelvin's gonna go right there. So I have T2 times 2.9 liters times 5 atmospheres equals 2.4 liters times 3 atmospheres times 323 Kelvin. All right, so now to get T2 by itself, I just have to do the opposite of it. Right now it's being multiplied by 2.9 liters and 5 atmospheres. I'm going to divide by 2.9 liters, and I'm going to divide by 5 atmospheres, or I'm divided by 2.9 liters times 5 atmospheres. Parentheses cancels. What you do to one side, you do to the other. All right, liters top and bottom cancel. Atmospheres top and bottom cancel. All right, so this time to find T2, we got 3 numbers at the top, 2 on the bottom. So I've got 2.4 times 3. Let's bring this guy over here. All right, 2.4 times 3 times 323 divided by 2.9 divided by 5. Oh, throw backspace. There will be shortening. Wait, no, we're good. Divided by. Oh, I see what it means. Can I backspace? I cannot. All right, so let's just try it again. Let's go CE. 2.4 times 2.4 times 3 times 323 divided by 2.9 divided by 5. All right, so in this case, our new temp will be 160.4 Kelvin. And taking a look, that's a huge decrease. But we know that temperature is directly proportional to both volume and pressure. And so both the volume and the pressure dropped. And so our temperature will drop by quite a bit. And that's a huge drop in temp. Just kind of give you guys an example of how to solve for temp. Anyway, hope that works out. I'll be around to answer questions.